Okay, so I'm going to go over this reactions and enthalpy worksheet that I gave you today in class. And we're going to review a little bit of potential energy curves along the way and look at table I and continue our discussion about the heat of reaction of chemicals, or at least chemical reactions. Okay, so these potential energy curves are potential energy over time. People think that different points of the curve is potential energy. No, they're all potential energy. Okay, and they're dealt with the energy in bonds. Since bonds aren't kinetic energy, they're part of potential energy. So two types of energy that exist in nature, of course, is kinetic energy, that's movement, plus the potential energy. And that equals the total energy, okay, of a system or universe or what have you. So this is about the potential energy due to the bonds, okay? And when you look at this reaction, this is methanol plus oxygen gives me CO2 and water. And we see that delta H is negative. This should scream to you that this is exothermic, okay? And the change in energy is being given off. It's exothermic, okay? So what does that mean? That means we must be starting high initially and ending lower for my delta H, okay, to go down 1452. Okay, that's why we would say that delta H, okay, is negative 14. Now it's joules per mole of something normally, but we'll just do kilojoules for now. Okay, so let's get rid of this line for a second. Let me extend it, okay, and we're going to go over here. So the difference of where you start and where you finish is your delta H. In this case, it's going down. Okay, it's equal to that. So it's going down. So this is the difference. So this difference of where I start and where I finish, and I should do this in another key color here, is my delta H. But the negative delta H, the change, means, hey, the products minus the reactants. We do that for delta H because we want to show a negative sign. So if the reactants have more energy than the products, then we should see a negative sign. Well, let's look at this value. The value from here all the way down to here is the potential energy of the reactants. And as we just said, because it's exothermic, it's going to be higher. This energy is the potential energy of the products. So a small number minus a big number will give us an overall delta H to be negative, and that's what we want. So that's why enthalpies are products minus reactants. Okay, now this tells us the state function, where we start and where we finish. But we also want to look at the pathway, and the pathway for this reaction would show potential energy changes looking something like that. Now, what does this mean? Well, we have something called the activated complex, and that represents the energy from the top of the hill all the way down. Okay, let's get rid of this delta H here because it's getting in my way. It looks like I get rid of too much and I feel bad, but now I can redo it. Not as pretty, but this is the energy of the activated complex. This represents the highest energy barrier. Now it could be two atoms that are repelling each other because of their electrons that are repelling, causing a force to go opposite. It could be the idea of the bond energies needed to break, or a combination of everything. But it's the highest energy barrier that we have to make a reaction occur. And the difference to that top of the hill to where we start is the activation energy. Activation energy. Okay? And that's the activation energy of the forward direction. This would represent the activation energy of the reverse. So this is the activation energy of the reverse. Notice it's bigger for the endothermic. It's exothermic this way, it's endothermic in the reverse. By the same number, the sign would be positive. Okay, Now we're adding a lot more than we need here, but I'm just showing you all the parts. Now, the last little bit of this is what would happen if I was to add a catalyst. And again, it's not part of this question, but I'm going to put it in here. Catalyst changes the pathway and lowers this hump, okay? And we'll talk specifically, but by changing this pathway, it actually lowers the overall activation energies, okay? And the reaction occurs faster because for the same amount of energy, if now my activation energy is now here, and this little arrow that I drew here is the activation energy of the catalyzed reaction. Okay, so the forward catalyzed, and this higher line would be the activation energy of the forward uncatalyzed. In class I mentioned as unmedicated higher and medicated. Obviously I would have another line here, and this would be the reversed catalyzed activation energy. Okay? Any case, catalysts lower the activation energy, lower this hump, providing a new set of reactions, a new pathway that's overall lowering this energy barrier. And for the same amount of available energy, you'll have more molecules that will be able to go forward and react. Okay? The best way to show that is to draw a little diagram like this. This represents a distribution of all the molecules' molecular speeds, called a Boltzmann distribution. So this is number of molecules, and this is speed. We know at one temperature we have an average, and we have some way above and way below. Now, if the activation energy is right here, this is the energy they need to react. E of A is activation energy. Only these molecules have enough to react. If I was to lower the activation energy and move it this way, now you can see there's a lot more molecules that have the energy to react, and they will. So by lowering that hill, or lowering the activation energy on a distribution graph, we can see that more molecules now have the energy to react, and they do so. Okay, let's go answer some of these problems now that we reviewed. Okay, so what is the value of the reverse activation energy if the activation energy is the forward is 560? Now, these are classic Regents type questions that require you, I think, to write down the numbers. Write a picture. When you get a question like this, they may not be a potential energy chart in front of you, so draw a picture. Okay, I know I've drawn a sloppy one now. But what's the value of the reverse activation energy? Well, if the activation of the forward is 560, and I'm going to draw a new one here, pretending that's not there, but if the forward activation energy, now I know it's exothermic, okay, negative delta H, so if the activation energy from here to here is 560, and I know the delta H from here to here, from my reaction here is negative 1452. So this is 1452. You probably can see that the activation energy of the reverse has to be the sum of these two lines, right? This is the delta H, and this is the activation energy from where you start to the top of the hill. So all I'm going to do is add them together. So 1452 and 560. So by drawing, okay, the diagram, it's easy to see that all I had to do was add that. Now some people can see it. I know that I couldn't. So at 11 here, 5 was 9 is 10. And there is my activation energy of the reverse. Makes kind of sense that the forward activation energy is lower if it's exothermic, unstable, but the reverse requires a lot more energy because these things are stable. Okay. What type of reaction is this? Of course, it is exothermic. Delta H is negative, and we're headed downward in energy. What's happening to the temperature of the environment? Temperature is increasing. Something in the environment is giving off heat, so the environment's temperature is going up. Okay, which of the chemicals in the reaction have the lowest potential energy? Well, it looks to me that the reactants have the lowest potential energy. Okay. Which chemicals in the reaction are the most stable? Mr. Stable had low energy. It's the reason why it's exothermic. I'm making something very stable so that energy has to be released. Who have the strongest bonds? We can look at this many different ways, but something very stable has the strongest bonds. It looks like I was talking about something, so wait a minute. Looks like I made a mistake, sorry. Which chemical in the reaction have the lowest potential energy? That would be the products. Don't know, I was saying something, my hand was doing other. And of course, the products are the most stable. And which chemicals in the reaction have the strongest bonds? We would say the products. Now, things that are stable have low energy, right? This has the lowest amount of potential energy compared to the reactants. And how did it get low? It had to release, and being low energy stable. But if you remember, party people, we had another way to look at this. And we did so by doing this. If you go in reverse, this is the energy to break the bonds. This is the energy to reform the bonds. It takes a lot of energy to break these bonds because they're stable. If you go in the forward, this would be the energy to break the bonds. This is the energy released to form bonds. So you can compare the amount of energy it takes to break bonds. Clearly, these chemicals here on the product side have the greatest amount of bond energies. Okay, so that's why the products have the strongest bonds. The more stable you are, the stronger the bonds, means you're going to stay in that state. It's pretty logical. Now, why is there so much CO2 and water in our environment? Well, because water and CO2 are very stable. It's a good thing. We wouldn't have a beach without it. We wouldn't be able to breathe. Okay, think about, we give off CO2. It better be stable to get to the plant so the plant can turn out the O2 from the CO2. So it better be stable. And all of our exothermic reactions, combustion reactions, produce these stable products. That's why they are exothermic. So the products of combustion, and combustion is an O2 molecule with some kind of carbon-based fuel giving CO2 and water. Okay? What is the value of the heat of reaction of the reverse reaction? Well, if the forward reaction, delta H, was equal to negative 14, is it 92? Where is my long-term memory? 1452, not good. Okay, that's the forward. All right, well, the delta H of the reverse is the same number, but positive. Why positive? Because if you go in the reverse, I'll put the units there, kilojoules. If you go in the reverse, okay, now you're climbing an energy amount to get there. All right. How many kilojoules of energy is released by the combustion of 0.5 moles of this methanol? Now, this is a classic Regents question, and I want you to look very carefully. Okay? This reaction is showing 1452 kilojoules, but it's 1452 kilojoules per 2 moles. If I want it per 0.5 mole, what would I do to that number? Right? This is an energy, and as we did calorimetry earlier in the year, we came up with energy, but we wanted to figure out the energy per amount. So this is the energy per 2 moles. Okay, they want a half a mole, so you'd have to take a 1452, and you guessed it, 1452, maybe, over here maybe, it's not running for me now. And divide by 4. And that'll give you your answer, and that'll be per mole. Okay? Little trick there. Okay, this is per 2 moles. But for 1 mole you'd have it, per a half mole you'd have to quarter it. All right? All right, now the next one, notice the sign is positive. Don't get crazy about the F. It's just a type of reaction. So I want you to do this one on your own. But I'm going to look over this, and I'm going to look at these questions for a second. Notice I'm asking per 1 mole of C2H4. This, my friends, is a synthesis reaction. We're making something from its elements. The opposite of synthesis is decomposition. So if you hear the word decomposition, it means we're breaking it apart. Okay? And you can draw that and answer those questions. And then you notice in the bottom here, we have some reactions based on ionic compounds. Now what this means is if I have sodium hydroxide dissolved in water, it makes ions, and look at this, energy is on the what? The product side or the reactant side? Well, if it's on the product side, it's exothermic, something to remember about. And of course, the solution gets warmer or colder. So we're going to go to table I now. Okay, going to finish this, and I'm going to go to table I right now. Okay, introducing table I in all its glory. Okay, well, table I breaks apart into 3 tables in my opinion. The first third is a combustion table. Notice you have some kind of carbon-based fuel with oxygen combining and making something very stable, CO2 and water. Making very stable products, it must be exothermic. Okay, kind of questions you can get from here is like the last one. What if I have 1 mole of methane? How much energy is released? And you would say 890. Now if I said I had a half a mole of octane, which is gasoline, how many moles released? You divide by 4 again, same kind of deal. So you have to be careful with this number and how much of this compound or other compounds they're talking about, because they could say, hey, upon every mole of CO2 that's produced in this combustion reaction, how much energy is released? And you'd say same number, because for every one of these, okay, that's how much energy. But what about per water here? For every 2 waters produced, what's the energy per mole? You divide by 2, because 2 is made from that total energy. To get per 1 mole, you divide by 2. So you've got to be careful here. The second half is a pour table. It really is trying to make something called a formation table. All of these reactions are called formation reactions or synthesis reactions, where we're making something from their elements. Notice aluminum oxide is made from aluminum and oxygen, and you're making aluminum oxide. So these are all synthesis, and notice they gave you values here. The reverse reaction is decomposition. You'd have the same sign, but you'd have the same number, but you'd change the sign. So for instance, the energy of formation, or the delta H of this reaction, is -3351 for aluminum oxide. But for the decomposition of aluminum oxide, you would say +33.51. Now something else you can do with this table, you can evaluate how stable elements are, or their strength of bonds. Case in point, let's look at aluminum oxide and let's look at NO. Which of the two has stronger bonds? Well, you may say, how do I do that, Mr. Grodsky? Well, draw yourself a potential energy curve, and you'll see this is very exothermic, which means the products are lower than the reactants, more stable. The more exothermic you are, the more energy you release. This guy is endothermic. It starts low and goes high. So it's not as stable. These have weak bonds. So the more exothermic you are in producing the product, the more stable and stronger the bonds. Be careful of this analysis. In the 2 that I compared, I had a 2 in front because I could ask you for the amount of aluminum oxide per mole that was released when formed, and you have to divide by 2 because 2 moles are made for that amount. Careful. So when you're comparing elements, just be aware of the 2 here, because I could say to you between ammonia, NH3, and C2H6, ethane, who is more stable? And you might say, well, ammonia is more stable, -91.8, but there's a 2 in front. Divide by 2 to get per 1 mole, and you would see that is lower, okay, or not as negative as a C2H6 per 1 mole. The answer would be C2H6. This would be the 46.4, okay? So that's something to think about. All right, the last third of the table are ionization reactions. These are salts dropped into a solid and breaking apart into their ions because they're all soluble. But look at here, they're exothermic or endothermic. They tell you whether or not if I dissolve potassium nitrate, by the way, that was a salt we used in one of our labs, it gets very, very what? Endothermic, right? Which means the solution gets colder. That means this chemical absorbs energy from the environment to break this apart, and the solution gets colder. NaOH, like we had in our the ditto, makes the environment warmer. So if you drop this in water, as we'll see in acid and bases, you'll see a huge change in temperature. Look at sodium chloride. This is what we used in our ice cream lab. I told you that the sodium ions and chloride ions actually lowered the melting point. Yes, that's true. But they also absorb some energy from the solution as well to make it colder. The biggest component of that ice cream lab was the ice melting, but also the sodium chloride dissolving takes up some energy. Okay, and looky here in the bottom. If you forget exo and endo, the bottom of this tells you that negative sign, a minus sign, indicates exothermic. So please try the rest of those worksheets. They shouldn't take you too long. We'll review. See you tomorrow.